All right. So a couple things before we get going. That Learn Smart assignment needs to be done before class on Wednesday. With the Connect assignment, I'm actually going to push the due date to be the end of the day Friday instead of the end of the day Wednesday. We'll cover some stuff today, I think, for like the last problem. A day and a half today should be more than enough time, but just to kind of, we don't have anything else to do immediately. So I'll push that off to this Friday by the end of the day. So I'll get that updated this afternoon. Also, before I forget, one thing I wanted to mention, for the online quizzes, we will have another one today. Start using something other than Safari. I don't know exactly if it's the combination of Safari with certain, like if it's on your phone or versus different types of computers, but it has issues picking up some of the math that I'll be putting on some of those online quiz answers or even in the actual question. So try to use Chrome, Firefox, Internet Explorer if you can. I haven't known those to have any issues, but Safari occasionally will have a couple issues. So keep that in mind moving forward. If there's no questions for me about anything, we'll kind of jump into stuff today. Let me make sure I get the chat pull up here. We good? Okay. So last week, we had been talking about the distribution of sample means, how we knew that the mean of those sample means would be the population mean, and how the variance of those sample means was the original variance divided by our sample size. Okay? So we can do a very similar thing for proportions. So before we jump into proportions, just kind of a reminder, we said the mean of our sample means was whatever the population mean was. The variance of our sample means was the original variance divided by our sample size. When we wanted to find the z-score for a sample mean, we then said take whatever cutoff value you're interested in, subtract the mean of your sample means, which that's just our population mean, and then divide by the standard deviation of our sample means, which could kind of be rewritten as, if I can get my marker to work here, it's a brand new marker, the square root of the variance over our sample size. Okay? So that's what we did last class, and we said we could kind of use those z-scores to find the probability we saw a certain value or less or more. So the sample proportion, so these proportions are going to be, you can think about for 1, 0 variable. So the proportion of a sample that is male, or a proportion of, I don't know, individuals with eye color green, right? Well, the binomial gave us the number of successes, or the number of times we would see that. Well, if I have a frequency or a number and I want to turn it into a probability, all I do is divide by the total number of observations there, or total number of trials, n. So what will end up being true is that for our sample proportions, the mean of our sample proportions, right? This was the binomial was the number of. If we want a proportion, we divide that by n. So the mean of our sample proportions is just whatever the true population proportion is. Just like the mean of our sample means was whatever the true population mean was. Now the sample mean for the variance for our sample proportions will just be whatever the variance was for the original population proportion, which would just be p times 1 minus p, because remember, this was the variance when we wanted the number of successes. Now that we want the number of successes out of, we just divide this by n. So the original variance we sampled from was p times 1 minus p. So the variance for our sample proportions would just be that original variance divided by whatever sample size we take. Very similar to what we were doing for the sample mean, right? So you can kind of imagine, if I go here, if I know that those are true, I can actually find the z-score for my sample proportions by taking whatever cutoff value for that sample proportion I'm interested in, subtracting the mean of my sample proportions, and dividing by, oops, I did not notice that typo in there, This should not have a caret over it. Let me see. So we'll copy this here. There we go. Dividing by the standard deviation of my sample proportions. Now we know that the mean of my sample proportions is just whatever the true population proportion is. And the standard deviation will be equal to the square root of p times 1 minus p over n. Right? Now we talked about last week with sample mean examples, we could actually, instead of plugging this in and making kind of a bigger equation to find the z-score, we could solve for this, kind of the intermediate step, and then just plug whatever number we find, right, whatever this ends up being, we could plug that number to the denominator. So the examples we worked through, I'll show you how we would do that both ways. Okay? But hopefully, you know, if we see this z-score, I want to write this out for the sample proportion real quick. Right? So we can see we're really doing the same thing. It's just that the notation's a little different because the mean of my sample means is whatever the population was. The mean for my sample proportions, well, that's whatever the population proportion was, right? We're looking at a different statistic now. And then the standard deviation of my sample proportions, we're going to have a slightly different equation than we did for sample means, right? But kind of where we start out to find a z-score, it's always take the statistic you're interested in, subtract the mean of that statistic, divide by the standard deviation of that statistic. Now, the standard deviation and the mean might be a little bit different, right, depending on what statistic we're looking at, but we at least start kind of at the same place. Okay? So, let's start out kind of working through an example with some actual numbers, right? So let's say I want the probability that if I flip a coin, I see 55 or more of those coin flips come up heads. It's a fair coin, right? So the population proportion should be what with a fair coin? Just 0.5, right? So I want the probability I see 55 or more heads. So what is my sample proportion cutoff that I'm interested in? 55 divided by 100, right? 55 out of these 100. So, you know, one thing I forgot also, the central limit theorem does apply because 100 coin flips is greater than 30. So just like with the sample mean, in order to know it's norm and distributed, we need to have at least a sample size of 30. Okay? Other than that, we can start to draw this out and think about what we're looking for here. Right? So I have a sample size over 30. I want to change the colors here because that marker is not right and very dark. So I've got my sample proportions, I know will be normally distributed around this population proportion, which I know to be 0.5. I then say, okay, the cutoff value I'm interested in is 55 over 100 or 0.55. And I want to know the probability I see that or anything more, right? 55 or more heads. So right away, I know this probability has to be less than what value? Well, the area to the right of the mean is 0.5. This is a smaller area, has to be less than 0.5. So what I'm then next going to do is I know I have a normal distribution, but I need to turn that into a z-value so I can deal with that standard normal distribution. So how do I turn this into a z-value? Well, that goes back to, this equation right here, right? So I'll show you two ways to do it. One, we can kind of use this. The second one, we'll use that. Okay? So I could just go ahead. The numerator there was use that cutoff value of 0.55. That was my sample proportion, cutoff value I'm interested in. Subtract the population proportion of 0.5, then divide by the square root of 0.5 times 1 minus 0.5, or the population proportion times 1 minus the population proportion, divided by my sample size of 100 there, okay? If I do that, I should get a z-score of 1. Right? Now, if I look at that z-score of 1 on the table, it's going to give me the area to the left. But remember, I wanted the area to the right, or the probability of seeing something that many standard deviations away from the mean or higher. Okay? So whatever area I find to the left here, I'm going to have to subtract that from 1. Okay? So I'll go to my standard normal table. I have a z-score of 1.00, or sorry, 1, which is 1.00. So 0.8413 is a probability of seeing that z-score or anything below it. So 0.8413. I want the probability of seeing that z-score or something above it. So I need to subtract that from 1, right? That's what, 0.1587, okay? So once I know I'm using this z-score, it's not too bad. Now another way I could have thought about this, and remember this z-score we found was 1. I could have thought about this using, and I'll get out of the way here in just a second, this format. Well, I know the mean of my sample proportions is always just my population proportion. And then here, I could have first found the intermediate value. So this was what, 0.55, this was 0.5. I could have first plugged this into my calculator, right? Once I had this, this ends up being, what is it? I think 0.05. I could have then just plugged that into my denominator, right? That's just kind of breaking it down into more steps. Before, we had this whole function kind of built into the denominator, right? So whichever way is kind of easier for you, it's fine, you'll get the same answer. And this kind of makes sense, right? If I had a z-score of 1, remember, the z-score is the number of standard deviations away from the mean that the value you're interested in is. Well, this was 0.05 away from the mean, and the z-score was 1. So what that's telling you is it's 1 standard deviation away from the mean. So if it's 0.05 away from the mean, the standard deviation must have been 0.05. Okay? Now, I'll never ask you to kind of work that out, back that out, but that general idea is floating around in the background there. Okay? All right. Also, if you want to move over, if it's easier to see. Okay, okay. All right. So let's work through one more example here. So what if I wanted the probability, instead of, I flip the coin 144 times, and I want to know what's the probability I see 66 out of those 144 come up heads or more. Right? So right away, if we just start drawing out what we're looking for, I think that's always the, that's where you should start. So I know that my sample proportions will be normally distributed because 144 is greater than 30, right? They're going to be centered around that value of 0.5 still, right? That was our population proportion for a fair coin. I could then think about what is the cutoff value I'm interested in. And this is where I'm going to need my calculator real quick because I can't remember this number. So I take 66 out of 144. That's that cutoff value I'm interested in. So approximately 0.458. Okay. I then plot that and say, okay, what's the probability I see? 0.458 or anything more than that. So right away, I know this area has to be greater than what? Well, the area to the right of the mean is 0.5. So I'm looking for an area that's larger than that. So I know right away this probability has to be greater than 0.5. Okay. So I can look at the possible values here. Has to be greater than 0.5. So C and A don't make any sense. Okay. So I can rule those out right away. Now, if I want to keep going with this, I know that I need to turn my normally distributed variable into a standard normally distributed variable, or these z-scores, right? So I'll take, right, that first thing I need for my z-score equation, if I go back here, and I'll do the one where it's all in one. So, right, we want the cutoff value we're interested in minus our population proportion, divided by the square root of the population portion times 1 minus the population portion, divided by our sample size, okay? So for us, that cutoff value was 0.458. Our population proportion is 0.5, square root of 0.5 times 1 minus 0.5, divided by that sample size, which is now 144, okay? If I do that, I'll end up with a z-score of -1. Now I could have first found this and then plugged it into the denominator. That was the other way we said we could do that, because really what this represented was the standard deviation of my sample proportions. But once I have that z-score of -1, well, now I can look it up in the table. Well, the table will give me the area to the left. I wanted the area to the right. So whatever I find from that table, I'll have to subtract it from 1. And just that first initial kind of reminder that, oh yeah, it has to be greater than 0.5, it'll prevent me from forgetting to do that last step. So we go here, we look up that z-score of -1, -1.00, 0.1587. So this area over here, 0.1587, we'll subtract that from 1, and then we'll have the area that we wanted, right? So in the slides here, kind of has that kind of laid out. Once we find that 0.1587, oops. Once again, I don't know why. Small typo here. I just want to make sure I fix these so I can upload these to make sure that everything looks good. Okay. All right, so we'll subtract that from 1, and we'll get 0.8413, okay? Which is greater than 0.5, which is what we originally said, right? Any questions on that before we keep moving? Yeah.
So our second number up top will always be 0.5.
So in these coin flip examples, it'll be 0.5. In other examples, it's going to have to be given to you, right? I mean, there's no way, unless you're given what the population proportion, like let's say I told you the population proportion of people with green eyes is, I don't know, or blue eyes is 0.18 or something like that. And then I said, from my sample, I saw that 20% of the sample had blue eyes. Well, there that cutoff, what was the probability I saw that or anything fewer? Well, there, your sample proportion value would be 0.2, but the population proportion was that 0.18 that you had to have been given originally. Yeah. Yeah, you'll always be given that value. And here the coin flip ones are a little weird because like you just inherently know. Yeah. Or I think the example in the homework, I think is something like you've got like a giant gumball machine and like the breakdown of green versus blue gumballs, or it might not be gumballs. I might be making that part up, but like the breakdown of what it looks like, and so the population proportion of red balls is 0.35 or something like that. Yep. All right. Any questions on any of that? That should all kind of relate to stuff we talked about last week. One more thing I wanted to show you before I forget, and you guys won't have this Excel file in front of you, but I wanted to kind of give you a little bit of insight here. So, and I don't know what this was. I was working on something here. So let's say I have this variable that is 1 if the individual in this data set is a female, 0 if not. Right. If I were to just find the mean, or in Excel, the average function of that variable, so I'm finding the mean of a 1, 0 variable. It'll return to me the proportion. What this is telling me is the proportion of people in my sample that were female is about what? 0.45, right? So if I find the mean of a 1, 0 variable there, that's really going to just return me the proportion, because if we think about what the equation for the mean was, it was add up all the values for that x variable, divide by lowercase n, or the number of numbers that we had. Well, for a 1, 0 variable, it would be something like 1 plus 0 plus 0 plus 1 plus 1. You know, we can go through the entire data set. Well, all this is going to do, the zeros don't impact my numerator at all. It's just going to count the number of females I had in that data set. It's then going to take that total number of females divided by the total number of people in that data set, right? And that's why taking the mean of a 1, 0 variable is going to return to you the proportion, right? So the proportion is just kind of a unique example of taking a mean, right? Has a slightly different equation for the variance there. Okay? Let me double check there's nothing here. All right. Excuse me. So we're going to really kind of switch gears here, and I'm going to have to talk a decent amount. I don't think we'll get to actually a problem on this today. So a lot of this is just going to be setting you up and trying to give you good explanations and good ways to think about confidence intervals, which is going to be a pretty big proportion of what we talk about for the next quite a few weeks, right? And lead us into hypothesis testing. So 99% of the time, we don't know what the population mean is. So we set all of this up, like all the examples we've looked at this far. I had a sample mean, and I was like, you know, I could find what the probability is. I saw that value because I knew what the population mean was, right? But I usually can't observe that population mean. Same kind of thing. Everything I say here for the means will be true about the proportions, right? Any parameter we're looking at, so mean or proportion. So what we want to try to do is get a sample that gives us a pretty good reflection of what the population mean is, a sample mean that gives a good reflection of the population mean. We've already talked about we want to ensure that our samples are unbiased. We don't have selection or non-response bias or kind of lying or, you know, whatever it is. But then we also want to make sure we have a small variance, right, on our sample mean distribution, okay? So what's one way we can kind of make sure that our sample mean is going to be more accurate or a better predictor about what the true population mean was? Well, remember, the variance of our sample means was equal to the variance of the data over the sample size. If I can increase my sample size like really high, I can drive that variance down. And if I get a really low variance, then the distribution of my sample means might look something like this, where it's centered around that population mean, right? And I know that values really close to that true population mean are really, really high, and that seeing values for that sample mean that are really far away from the population mean are very, very low, right? So this is good if I can only take one sample, because when I can only take one sample, I'm not seeing all these different values, I'm only seeing one. So I want to ensure that that sample mean has a high likelihood of being a value that's very close to the population mean. How can I do that? Take higher sample sizes, get like a really narrow distribution for these sample means. Sorry. Yeah, no, I said that right. Okay, so with this in mind, what we also want to do is be able to say, look, I know that I can't observe this true population mean. I can take a sample and I can try to use that to guess, or as a best guess, I should say, of where that true population mean lies. But let's say I take a sample of size 40, central limit theorem's met, I find a sample mean of 45,000 for income in the US. Well, look, I found 45,000, but I know that even if, right, the true mean was, I don't know, 45,500, it's probably not very unlikely that from a sample, I see 45,000, I said 4,500, sorry. The true mean was 45,500. It's not very unlikely that from a sample, that I see a sample mean of 45,000. That's not very far off, right? So the problem is I know my sample isn't going to be exactly right. In fact, I know that there's no chance, I shouldn't say no chance, but in theory, the probability that I see a sample mean exactly equal to the population mean, well, remember, if it's a truly continuous random variable, the probability of any one value is 0. So there's really no, like, I know built in that my sample mean is going to be a little bit off of what my true population mean is. So how can I use that sample mean to make a statement about what the true population mean could be? Right? And I'm going to skip this example because I don't like it, and we're not going to even be able to get to it today anyway. So we can kind of ignore, where was it, this slide for right now. So let's say what I want to do is, based off that sample mean of 45,000, I want to be able to say, well, look, I know that it's probably not exactly the population mean, that's a little off, but I'd feel really comfortable saying that the true population mean is probably somewhere between 40 and 50,000, right? Based off the evidence that I saw, 45,000 was my sample mean. I'm okay saying with a pretty high level of confidence, the true mean is probably somewhere in between 40 and 50,000. So what I've done is I've created this range of values that I can say with a certain level of confidence, the true population mean is within this range, right? And that range was based off of the sample evidence I found, or that sample mean, okay? Now, when I'm saying things like a certain level of confidence, you know, we'll eventually get to this, but typically we say things like with 90, 95, or 99% confidence. Those are like the benchmark values we have. We could say things with 83% confidence. It's just kind of a goofy number to choose, right? It doesn't have a whole lot of significance to us. Kind of our benchmark values, 90, 95, 99. All right. So when I gave you that example, I went from 45,000 as my sample mean, and the range of values I created was 40 to 50, right? So I had a lower bound of 40,000, an upper bound of 50,000. So what I did there was I went the same distance below my mean to get the lower bound, and the same distance above that sample mean to get my upper bound, right? So I'm basing this range of values, I'm centering it around whatever the sample evidence I found was, or whatever my sample mean was, right? Different ways of saying that. Okay, so I'm saying, look, the sample mean is the best evidence I have about what this true population mean is. I know that it probably is a little bit off, but it's the only place I have to start. So I'm going to start at that sample mean and go a certain amount above and below it and say, okay, within this range of values, I'm X% confident that the true mean lies somewhere in between these two values. Okay? But how do we choose that W? I chose an arbitrarily one and went 5,000 above and below just to kind of set this example up. But there's actually a method, step by step, that we can follow where we can come up with a value for W here that would represent, or that we could guarantee with 90% confidence it's in between this lower and upper bound, within 99% confidence it's within this lower and upper bound. So what is that method? Right? Well, to get to that method, we're going to take a step back to something we've already talked about. So we know the sample means are normally distributed. So we can use what we know about this normal distribution and kind of standard normal distribution. So let's say I want the 95% confidence interval. Another way of thinking about this is, and I'll skip down here a second just to give you some visuals here. If I were to go 1.96 standard deviations below the mean, 1.96 standard deviations above the mean, if I wanted an area of 0.95 in between those, I would know that the area outside of that would have to be a total 0.05. Since I'm going the same amount above and below the mean, those areas have to be the same, or that each area is 0.025. Now, where did that 1.96 come from? Well, oops. If I go to the table, and I know the area I want in the tail is 0.025, I hunt around for it. It's right here. So negative 1.96 would give me that area of 0.025 in that lower left tail. Right? So where that came from, right? The whole kind of setup was if I wanted the 95% confidence interval, I know that I want to go a certain number of standard deviations above and below that sample mean I see, right? Now, well, I'll take a step back on. Let's say it this way. If I were to go the same number of standard deviations above and below the true population mean, I know that if I went 1.96 standard deviations above and below, the probability that if I were to take one sample, the probability that sample mean is somewhere in between 1.96 standard deviations above and below the true population mean. That probability would be 0.95. So the probability I see something further than 1.96 standard deviations away from the mean would only be 0.05, but it could be below or it could be above. So the probability it's more than 1.96 standard deviations above the mean is 0.025. The probability it's 1.96 standard deviations or more below that population mean is also 0.025. Okay? And that came kind of directly from the table finding that 1.96, right? Once we knew the area that we wanted in the tails, we could look up and find the z-score that would give that to us. Remember, the z-score interpretation is the number of standard deviations away. So that's why when we look up 0.025 and found the z-score of negative 1.96, well, that's why we know we're going 1.96 standard deviations away from that mean. Okay. So running with this same confidence level, this confidence interval of 95%, if I think about if I were to take one sample, right, there is a 95% chance it's in between 1.96 standard deviation above and 1.96 standard deviations below that population mean. So let's say, and then a 5% chance that it's kind of in this red area, right, even further away. Let's say I take a sample, I calculate the sample mean. If I were to then add and subtract from that sample mean 1.96 standard deviations, so I go 1.96 standard deviations above, 1.96 below, what's going to always be true is that for this sample mean here, it's going to include, right, that confidence interval includes the true population mean. If I take another sample mean, it's over here. Well, when I build a confidence interval around that, it also includes the population mean. Right? Any sample mean value I see within this blue range here, that's within 1.96 standard deviations above, or within 1.96 standard deviations of that population mean, any sample mean in this blue area would have a confidence interval that includes the population mean. If I take a sample and the sample mean I see is somewhere out here, when I build a confidence interval around that sample mean, it won't include that true population mean value, okay? So 95% of the time, I'm gonna get a sample mean where if I build a confidence interval around that sample mean, it will include the true population mean. 5% of the time, I will see something such that if I create a confidence interval around that sample mean, it won't include the population mean, okay? And kind of give you a little bit of intuition behind why. So let's think about going 1.96 standard deviations below the population mean, right? So when I was kind of finding that, I was going 1.96 standard deviations below the mean. And what that was doing was that was creating my cutoff here, right? So if I see a sample mean that's somewhere out here, right, I know that this is more than 1.96 standard deviations below, right? This is more than 1.96 standard deviations below the mean. So if I then add 1.96 standard deviations to this value, right, it won't take me quite up to that population mean, right? Essentially, you can think about it this way, right? X bar here would have to be equal to something like the mean minus, well, more than 1.96, so maybe, I don't know, 2.4. Well, if the sample mean is 2.4 standard deviations away from the population mean, and I then add 1.96 standard deviations to it, well, I'm still going to be, what? negative 0.4-ish away from that true population mean. So that's why every sample mean value I would see in this red area, when I add 1.96 standard deviations to it, it doesn't quite get me back up to that population mean. Okay? So the idea of our confidence intervals are, if I build a confidence interval around my sample mean, I know that 95% of the time, that sample mean's confidence interval will include the population mean. And then 5% of the time, it won't. So that's why if I know that I'm going to be failing 5% of the time, that's why I'm saying it with 95% confidence, right? Because I will be wrong 5% of the time. Excuse me. Even though these values down here are very unlikely to see for the sample mean, they still can happen, right? All right. Any questions on that before we kind of keep moving here? Okay with this? Like I said, a lot of the today we'll just kind of be setting things up, working through some actual problems next class. Okay. So one thing that I want to touch on is some kind of terminology we'll start using. So let me just go through this. So I'll start referring to this thing called alpha, right? So we can say things with different levels of confidence, 90, 95, 99%. Those will be our kind of 3 benchmark values. Alpha is essentially going to be the area that's in our tails, right? So if we go back up here, for the 95% confidence level, the total area that was like in our tails or the area outside of our confidence interval, right? The total area that would be outside of that interval is what? 0.05, right? So for the 95% confidence level, alpha is 0.05. So there's 2 different ways to think about alpha. One, you can think about the less technical way. Whatever confidence level I have, what percent is outside that level, or what percent is outside my interval? So for the 99%, the percent outside the interval would be 1%. And then alpha is just that, but in decimal form, right? So 0.01. 95%, the percent outside of that interval would be 5%, in decimal form, 0.05. Probably the better way to think about it is, when I'm thinking about the confidence level I want, alpha really represents the proportion of the time that I will construct a confidence interval that doesn't include the population mean, right? So if 95% of the time I have a sample mean where the confidence interval does include the population mean, 5% of the time I wouldn't, but that is a probability would be 0.05, right? So different ways of thinking about alpha, but you can kind of see the connection there, right? Whatever confidence level you have, alpha is just the area that's would be kind of outside of that confidence interval, but in decimal form. Okay. Any questions on that? And you could work in reverse too, right? If I know that alpha is 0.1, well then I know the area that's kind of in between the 2 values, or the area within my interval is 0.9, which would be, as a percentage, 90%. Right? So we can work in either direction there. So before I show you that, I want to go through one more kind of example to kind of set this up. So let's say instead of the 95% confidence level, let's say I wanted the 90%, right? So if I wanted the 90% kind of confidence level, right, what I can think about is what I'm really wanting eventually is I want to go a certain number of standard deviations above and below my sample mean, or my population mean. But I know that I want to go the same number of standard deviations above and below. So whatever the z-score is, the positive and the negative, in absolute value, they'd be the same. Right? And I know that the probability I want in between those is 0.90, right, for the 90% level. So if the area in between these 2 z values is 0.9, what area has to be outside of those z values? Well, if the area under the curve is 1, and the area probability in between these 2 values is 0.9, the total area kind of in my tails or outside that interval would be 0.1. But I have 2 equally sized, right? This is a symmetric distribution. right? The Z values, and they're centered around 0. So if I were to fold this across the mean, it's symmetric. This would fold exactly on top of each other. So I know that these two areas are exactly the same, okay? So if the total area, alpha, is 0.1, how many standard deviations away from the mean do I need to go to make sure that I have an alpha of 0.1? Well, if alpha is 0.1, the area in each tail is actually alpha over 2, or 0.05, right? I would then look up 0.05, and I could find that z-score, right? So if I do that, I did not mean to do that. If I do that, I want to find 0.05, so I start looking. It's in between these two values. So negative 1.64 and negative 1.65. So I'll take the higher of those two, negative 1.65 below, and then positive 1.65 above, right? So I know if I were to look at values that were 1.65 standard deviations above and below the population mean, 90% of the time I'll get a sample mean where if I built confidence intervals around that sample mean, it would include the true population mean, right? But kind of what I want to work through here is to think about alpha is the total area in the tail, but to get that z-score, I need to look up alpha over 2. So when we actually formally write out the equation we want for the confidence interval, I can stop here. We'll build our confidence interval around whatever sample mean we find. We will then go a certain number of standard deviations above, so adding this to get our upper bound, and a certain number of standard deviations below, so subtract this to get our lower bound. And when I say a certain number of standard deviations, well, that z-score represents how many standard deviations away. So if I want to be 2 standard deviations away, I don't just add 2, I add 2 times whatever the standard deviation is, right? I want to make sure I'm 2 standard deviations away to get my upper bound, right? Now I said 2 there, I was just using that as a place mark kind of value. The actual value we want for z here, or the actual number of standard deviations we want to go away, is whatever gives us alpha over 2 in each tail. So remember when we had here, whatever z value gives me alpha over 2 in each tail, right? So whatever gives me alpha over 2 in each tail, that's the z value that I want to use to build my confidence interval. And then I'll multiply that by the standard deviation of my sample means, right? Because I'm looking at the distribution of my sample means, so the standard deviations away that I want to go are whatever the standard deviation of my sample mean is. Okay? So as a reminder, I could also then think about writing out for my confidence interval. So I'll add to get my upper bound, I'll subtract to get my lower bound. So instead of, right, writing that as the standard deviations of my sample mean, I know that this is equal to the square root of the original variance of the data I sampled from divided by that sample size. Okay? So another way of kind of writing out that confidence interval equations here, where when I add, I get my upper bound. When I subtract this, I get my lower bound. And what I'll often refer to this as, even though it's not technically correct unless we're dealing with proportions, I'll use this and refer to this as my margin of error. Okay? So you add your margin of error, you get your upper bound. When you subtract your margin of error, you get your lower bound. Like I said, that's not technically correct unless we're dealing with proportions, but that's okay. Okay? All right. Where are we at in time? Okay. So I want to start out, I want to lead us up into something for the next class. So if I think about this confidence interval, if I want to say something with 90% confidence, right, then I'm going to have, that's the one we just looked up. That was the z-score of 6.5s. that gave us alpha over 2 of 0.05 in each tail, okay? If I want to go to a higher level of confidence, what's going to happen? Well, a higher level of confidence, right? So going from say 90 to 99, what's alpha going to be at the 99% confidence level? Well, the 99% confidence level, what percent's outside of that? 1% in decimal form would be an alpha of 0.01. So there's going to be alpha total in the tails, but now the area at each tail is going to be alpha over 2. So 0.01 divided by 2 is 0.005. So now the new area I want in the tail is 0.005. Well, to get a smaller area, what's going to have to happen to these z-scores? They're going to get larger in absolute value, right? So if I want to say something with a higher level of confidence, what's going to happen is I'm going to end up with these higher z-scores where if the z-score gets higher, I'm adding and subtracting a larger amount to my sample mean. So higher levels of confidence are going to be wider confidence intervals, right? Because it's going to increase that z-score and kind of add, subtract a larger margin of error to my sample mean, or kind of widen that interval. Or said differently, if I want to go to a lower confidence level that's working in reverse, then I would have a smaller interval, right? And that kind of intuitively makes sense. If I say something with 90% confidence, in order to say it with 99% confidence, I have to include more possible values, okay? All right, so I think we'll end there for today. We'll kind of pick up on this discussion, talk about some other things that will influence our confidence intervals, work through a few problems with some actual values to them. We'll also do a little bit of work in Excel probably on Wednesday, okay? Once we get through some of that Excel work, you'll start to be able to work on the rest of that Excel assignment, okay? If there's no questions, I'll see you guys on Wednesday.